In this video, we're going to look at naming alkanes. We're going to start with the simplest alkanes. So we're going to start with straight chain alkanes, and alkanes are saturated aliphatic molecules. And so saturated means that it only has single bonds, and aliphatics are organic molecules that are not aromatic. So because we haven't actually been able to look at aromatics yet, that doesn't mean much to you, but that's the kind of either or. Either it's aliphatic or it's aromatic. Alkanes are aliphatic and they are saturated. Now, the naming of alkanes is going to be related to the number of carbons in the parent in the chain. So if it's got one carbon, it's a meth. If it's two, it's an eth. 6 is like a hex. 8 is oct. 9 is non. 10 is decane. Probably the ones that are the most difficult to remember are prop and bute, because they're kind of not like geometrical things like pent, hex, hept, oct. Those are pretty easy from your math classes to remember, but you really kind of want to know the first four for memorizing sake. You're going to see them a lot, so it'll start to click in once you've done some practice, but that's pretty important. Now, molecular formulas for all alkanes are going to kind of follow a pattern. So if we look at methane, because carbon has 4 bonding electrons, it can make 4 single bonds, and so it's going to be CH4. Ethane is going to have 2 carbons bonded together, and so it's going to have all the other bonding electrons forming single bonds to hydrogens, and so it'd be C2 and then H6. Well, we've got a little pattern here that shows us that it's an alkane and that it's a saturated hydrocarbon, where it's CnH2n plus 2. So if this was, the N is 2, so Cn is 2, H2n would be 4, plus 2 is 6, and that's how we come up with this number. So if we apply that to butane, for instance, butane has got 4 carbons. It would have 4 times 2, so 8, plus another 2 is 10. If I went to heptane, C7, H7 times 2 is 14, and plus 2 is 16. And so the advantage to understanding that relationship is I can actually spot if it's a saturated aliphatic if I know that relationship, right? So if I had C50, H100, I know it's not saturated, because if it was saturated, it'd be C50, and it'd be H100 plus 2, so it'd be 102, right? And so, I mean, this doesn't come up exactly in this kind of example, but it's kind of helpful to be able to spot that this one that I've highlighted here would be a saturated molecule, and that this would be unsaturated, because it does not follow the little rule that we had up here. Now, what we've got here is our first introduction to the idea of a homologous series. A homologous series is a series of similar molecules that are only different by 1 carbon in length. And so methane, ethane, propane, butane, pentane, hexane, etc. Those are all saturated alkanes, and they're straight chain alkanes. And because they're all comparable, that makes them comparable because they've got similar kinds of properties. Because they are all saturated aliphatics and that they're straight chain, I can compare the boiling point of propane and heptane, because there are no other really things to compare other than the size of those 2 molecules. And so when we look for comparison for kind of behaviors or properties, we like to compare either homologous series, so things that are very similar but different in size, or we like to compare things that are the same kind of properties but something else is different. So it'd have the same molecular formula, but something else has changed, so that it makes it so we can compare apples to apples. So the homologous series is just is a group of molecules that have similar structures and properties but differ by 1 carbon. I'm going to show you how we're going to draw some alkanes. There are 3 different kind of standards. We have a structural diagram. So for butane, has 4 carbons, and a structural diagram shows each of the hydrogens. and it's pretty like demonstrative. It shows everything, shows all the bonds, shows all the atoms. Condensed structural diagrams are going to show similar stuff, but it kind of compresses it so it's a little tidier. So heptane is 7 carbons, and you can imagine that if we drew in every single hydrogen, it'd be really busy. Like it'd be just this kind of a mess. And for 7 of those, that's just too much. Like people don't want to look at that. So instead what you do is you condense it. So you start grouping things together. So this would be CH3. Now, important to note that there's 1 bond here, so we get 3 hydrogens. And the next one has 2 bonds, so it's H2. And the next one has 2 bonds, so it's H2, 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 H2. But the last one has only 1 bond, so it's CH3. You can actually, apologize for that, you can actually condense this even more. So sometimes you'll see something like CH3, and then if we look in here, you get 1, 2, 3, 4, 5 CH2s grouped together. So you get CH2 brackets 5 CH3. So it's possible to even condense it more, but the condensed structural diagram is basically just trying to save some space and make things more tidy. Line structural diagrams show quite a bit, but it's a different way of showing it because the end of each line is a carbon and the line represents a bond. And so octane, if I was drawing the condensed structural diagram, is going to be like so. And it's a mess. 1, 2, 3, 4, 5, 6, 7, and then the 8th one. Even that's a lot to draw. So instead what they do is they make each carbon is the end of a line. So I've got those 2 carbons are represented here. And so this is 2 carbons, 3, 4, 5, 6, 7, 8. And so each of these carbons is represented at the end of a line. 1, 2, 3, 4, 5, 6, 7, 8. And that's a line structural diagram for octane. Here are some examples for C6H14. So for a straight chain alkane, this is hexane. Try doing those yourself.